Bon, bah on va commencer. Voilà, c'est un plaisir pour moi d'accueillir Brian Burg aujourd'hui. Donc Brian, il a fait sa thèse à ETH Zurich, d'accord, en Suisse, et puis un postdoc à Boston. C'est là qu'on s'est rencontrés, d'accord. On a même été colocs ensemble. Ensuite, il est revenu, c'était à Zurich, chez IBM. D'accord. Donc il travaillait sur les instrumentations, les petits capteurs à toutes petites échelles quand il était à Boston notamment. Et puis après chez IBM aussi dans le domaine du capteur et de l'instrumentation à toute petite échelle, d'accord, transfert de chaleur et autres. Et puis il a basculé dans le côté obscur de la bioengineering, d'accord. C'était au 2015, d'accord, à ETH Zurich, où tu as travaillé sur un foie artificiel.
Système à perfusion.
Système à perfusion, avant d'appeler ça foie artificiel, voilà. Et puis, il y a 1 an et demi, il est revenu en France. Donc, c'est ce qu'il va nous présenter aujourd'hui dans la start-up CorWave. D'accord. Et ça va être la thématique d'aujourd'hui. Donc, je te laisse la parole, Brian. Oui, ça va être en anglais. Brian, il est luxembourgeois, américano-luxembourgeois. Il est plus à l'aise en anglais qu'en français, donc on va faire ça en anglais. Puis les questions, vous aurez le choix, anglais ou français. Voilà.
All right. Thank you, Arnaud, for the introduction. I hope I will live up to the expectations. Good morning, everybody. This is my first presentation I'm giving where I'm broadcasted live through YouTube. So I would like to say hello to my colleagues in Clichy who are watching right now and anybody else who may be watching. What I'll be presenting today is our technology at CorWave. I'll go into the details of all that. But the piece of advice I once got when you're invited to a talk is know your audience. And it's been a few years since I've done my mechanical engineering studies, so the name d'Alembert rang a bell, but I really couldn't pinpoint it anymore, I have to be honest why. So I went into the great book of knowledge, also known as Wikipedia, and I saw you guys here have a little bit of a cultural advantage because what was taught to me in the name of wave equation, or the German equivalent, because I did my studies in German, you commonly refer to here as D'Alembert equation. So that helps you to remind why he is, amongst others, known for. But that sort of presented me an opportunity, or on a silver platter, how to entitle my presentation, which I named here, Supporting the Heart with the Help of a Wave. Because that is really what we do. And then I came to think about it, and I was surprised that we've never really been in contact, the company, CorWave, and the Institut d'Alembert, who does lots of work on mechanics and waves, and you'll see a bit more of that in this presentation. A bit of a disclaimer before we get started. I am, some people would refer to, on the dark side of things, as opposed to academia. I work for a company. I don't have the liberty to disclose everything which we're doing, so I will be a bit light on the technical side. So it's not going to be your classical presentation, but nonetheless, I hope I can keep you interested in what we're doing. I didn't know that Arnaud will give such a detailed presentation of me already, so just that's the other part of things, know your audience. Well, you might also want to know your presenter. So as Arnaud said, I was born and raised in Luxembourg. A bit more than 15 years ago, I went to Zurich to do my studies in mechanical engineering, focusing on thermodynamics, heat transfer. I did a thesis in sensors, electrokinetics, nanotechnology. Then I went over to Boston, a postdoc where I met Arnaud, where I was researching the fundamental transition between heat conduction and heat radiation, a very interesting and complicated problem. After that, I wanted to get back into more of an applied domain again, so I jumped back over to Zurich to one of the research labs at IBM, where we were working on water cooling of data centers. They had a big ecosystem on what they called hot water cooling. So you use warm water to cool, you still increase the temperature a bit, and then you use this warm water in an ecosystem for a range of other applications, ranging from desalination, heat pumps, and the like, and we applied the technology to concentrated solar cells. Anyways, I did that for 2 years, and then I had the opportunity to lead a project at a newly established institute between ETH Zurich and University of Zurich, where the project was to develop a perfusion system for a liver. So we had livers and we needed to develop a blood flow system which supplied the liver with blood. And there were already biologists and physicians on the project, and they specifically needed an engineer who understood the work of creating a fluid loop. And if it's water or blood, I mean, a few things change, but in the end, you still need pumps or valves. And so that's what we did. And then about a year and a half ago, I came to Paris because it was time to join my young family. And I set foot here in Paris and joined CorWave pretty much exactly a year ago. So I made the assumption that pretty much all of us in here are mechanical engineers, so I'm allowing myself to give you a little primer on the heart from an engineering point of view. And the heart is essentially a displacement pump, a positive displacement pump, and we have two of them in our body. We have the right side and the left side. And the right side pumps the blood to the lungs, and the left side pumps the blood to the body. It's essentially what it is from a mechanical point of view. A few details: the average power output of the heart in terms of hydraulic power, so flow times pressure difference, is 1.5 watts. Obviously the heart is pulsatile, so it goes, the power output goes up and down, but the average is 1.5 watts. The heart beats roughly 40 million times a year, depending if you do, I guess, more sports or less sports. But that's sort of a good average. And a sort of interesting number I find is that it takes 16 seconds for the blood to loop the body. So the blood flow through the heart is roughly 5 liters per minute. And then if you sort of track it, it takes 16 seconds on average to cross the body. Now, obviously there can be problems with the heart diseases, and the issue we're focusing on is what you call heart failure. And heart failure is essentially nothing else than the inability of the ventricle, which is a part of the pump, to either eject the blood or fill with blood. So basically opens up and pushes out. So whenever there's a mechanical problem in the sense that it can't fill or it can't push out, you have heart failure, and you're not able to deliver enough blood to the body. So there's a whole range of symptoms, let's see if this works, which describe heart failure. And these patients can be rather sick. Obviously, it depends on the degree of heart failure, and then you have charts like here, which defines the level of heart failure and what you can do against it. So you have sort of the first level where you just know you're a risk factor, maybe because of family history and whatever, and you just need to monitor it, not much to do. And then you have the different stages. Now, if you jump all these stages, because I'm not a physician and don't know all the details here, if you just go to the last one up here, we see this is hospice. This means essentially nothing can be done for you anymore. And the last step before hospice is where we try and come into play, is up here is VAD. That's a ventricular assist device, so it's a device to assist the heart, or transplantation. It's sort of, this is done at the last stage, at the last possible stage of the patient to try and help him, because these are very invasive procedures. Now, what is a ventricular assist device? Well, it is a device which you implant underneath the heart, and its purpose is to help the heart pump. I would say it as simply as that. And often these devices are used what you call bridge to transplant. So if there's no transplant available, you implant this device until a heart transplant is available, and then you carry out the transplantation on the patient. Or if for whatever reason the patient is not on the transplant list anymore because of some conditions they have, or they're too old, or for whatever reason, they're also used as destination therapy, the last therapy available for a patient. Now, I'm going to go a little bit into the history of these ventricular assist devices, how they evolved over time. So you see over here the evolution of the first devices and the current devices. And the first devices which were actually made were pulsatile devices. You can see them right here. They were approved around the year 2000, and they allowed to have a pulsation in the body. However, there were many reliability issues with these devices. They had mechanical bearings, and just the devices were not very reliable, and simply the devices failed, which is usually a fatal condition for the patient. So efforts, well, were ongoing at that time already to try and obtain more reliable devices, and they essentially focused around two approaches, axial flow and centrifugal flow devices. The axial flow devices were a bit earlier, where you basically have the axial flow of the blood which comes in here from the heart, is accelerated through the pump here, and then is redirected into the aorta. These devices function very well on a reliability point, from a purely mechanical reliability point of view. They function rather well. There may be some issue with what you call thrombosis, which are blood agglomerations or coagulations of blood. But if you just speak from a mechanical reliability, robustness point of view, these devices are very good. And a bit later, but sort of similarly, in a similar time frame, another type of device was developed, which are centrifugal flow devices, which are a bit smaller in size and which don't have any mechanical bearings. So there was always the expectation, if you have a mechanical bearing in the pump, that the bearing will fail at one point because of the previous experience which was had. So these pumps have hydrodynamic levitation, magnetic levitation, to avoid the bearing and thus avoid some side effects which may be possible. And this is the promise of these devices which are currently entering the market. This is BT Bridge to Transplant, was approved in 2012. For this particular device, destination therapy is still ongoing. So this is the current state of the field. Now, the big question today is this first generation is not used anymore, and it's basically axial flow and centrifugal flow devices which are on the market and which are being implanted into patients, and studies are currently ongoing to evaluate which device actually performs better. And here are the results of a very current study. In fact, it was officially published today. Online, it was published a month ago, on the latest results comparing these two technologies, more precisely comparing two different pumps. And if you look at them, what they often look for is survival rates after 2 years. And if you look at the axial flow pump, the survival rate after 2 years is roughly 3/4. And of the centrifugal pump is 80%. So in the end, there is an improvement. One has to say there's an improvement for the patient, but it's not hugely significant. But still, if one would look at these numbers, they are not bad in comparison to what I'm going to show you right now, which are the side effects or the adverse events which also come into play, but which are not fatal for the patient. So you see here, this data is only for survival. How long does the patient survive? But there are many associated side effects, adverse events, which many patients experience on these devices, essentially over 80% within 2 years, which require rehospitalization because on the one side, the smaller number of cases, there's an issue on the pump, but mostly because they have strokes or some type of bleeding, internal bleeding. And if we just to look at the current problems, which are not really resolved, if you look at the bleeding problem between the two types of pumps, so it's broken down here, any bleeding, gastrointestinal bleeding, bleeding which leads to surgery on the pump, there is no difference, significant difference in the percentage of the patients which are affected by this. And this sort of, well, is troubling, because you implant this device into patients and you say, well, you have an 80% chance of living after 2 years, and also you have an 80% chance of experiencing rehospitalization because of a severe adverse event. And obviously people think about why this is, but these are complicated problems, because how can you link a stroke or internal bleeding to a medical device? And one of the hypotheses is, and there's many people who support it, but it's an hypothesis, is it's because these devices do not provide pulsatility. So they're continuous flow devices. So if you try and take the pulse of these patients, you will not feel a pulse. And the hypothesis is that it is a chronic condition which arises after several months under these devices, that the human body must have a reason for having a pulsatile heart, and that this is a feature which is lacking in these devices. So CorWave's mission is to bring back pulsatility as the first devices, but let's say with the increased reliability and the smaller size. And people are actively thinking about this, and this is a paper which was already published in 2014, which makes the hypothesis that it appears as though the ultimate solution will be a return to recreating our natural physiology. So to reintroduce pulsation into ventricular assist devices. And this is what we're trying to do at CorWave. And the way we are trying to do this is that we're completely changing pumping principle. The two current technologies on the market are axial flow devices, centrifugal flow devices, but they're all rotating devices. They're rotary pumps. And the problem with rotary pumps is once you start rotating them at high speed, they have high inertia, and it's difficult to accelerate them and deaccelerate them to introduce pulsatility. You lose efficiency, you have to put in more power. And so they have inherent limitations in the technology to create true pulsatility. And the premise of CorWave is to use a different technology based on an undulating wave, which you can see right here, sort of analogous to a fish, to propel the fluid, with the difference of the fish that our membrane remains in a fixed position and we accelerate the fluid. We have a nice image to demonstrate that this is, or video, this is one of our membranes in the fluid, so you can't really see the fluid displacement, but this is how the membrane moves, and we have an acceleration from this side of the fluid to this side, and this is our pumping mechanism. Now, if correct, yes. And if we integrate all this technology into a device, and so I'm taking several steps here, we have something like this. So this would be, well, this is our ventricular assist device, our implant, which can perform true pulsatility, something which you cannot do with the rotary pump. So you see it almost comes to a complete stop, and then we can turn it on at a frequency of about 1 beat per second. Yes. And this is, well, what we based the company on. So to give you a bit of background on the company, it was founded in 2012, right here in Paris. We are currently a growing team of 45 and more employees. We have quite a number of interns too. We're always open for internships. To date, we have raised over 20 million euros. So it's a serious endeavor we have engaged on, but it is also a domain which requires lots of effort, and we still have about, well, easily 5 years to go until we would be on the market. And our products are based on, well, several years of research and development and several patents. So a bit for the anecdote, it's an engineer from Arts Métiers who developed this type of pump based on an undulating membrane, but he did the developments for industrial applications. And the idea of CorWave was to downsize these industrial applications and make them implantable, so we would have an LVAD, and thus avoid all the side effects from the current devices. And so that's the origin. So I said pulsatility is important, and then the other aspect which we believe will be improved with this device is hemolysis, shear stress on the blood, that the blood damage will be reduced just because we have less, we have no rotation in the system. So we are currently what we call in the preclinical development of this LVAD, left ventricular assist device, and we're in the development of a second product for partial support, which would be implanted in patients who are not as severely sick as those who need a left ventricular assist device. So I started going to these presentations or these conferences on what you also call mechanical circulatory support. People from companies have to give disclosure, so you have the disclosure that I am an employee by CorWave. I'm not in academia anymore. It changes things a little bit. And down here you see a list of the investors in our company. So Right now I will proceed to explain in a bit more detail the technology of the pump and to explain to you how it works and the different issues which we face, the different backgrounds we have in the company who tackle these problems. So this is the implant. The implant is everything which is implanted into the body. My team is responsible for the development of the implant. It has to be biocompatible, implantable, it has to work, we have to follow all the regulations. But because these are devices which require a considerable amount of energy, we still have a so-called percutaneous lead which comes outside of the body, and the controls of the system are on the outside of the body, including the batteries. So the patients typically need to recharge their batteries anywhere from every 4 to 6 hours, and they have multiple battery packs at night. They hook themselves up to the wall essentially, and that's a whole different group who takes care of that. Now inside the implant is basically made up of two things: an actuator, a motor, and the pump head. I highlighted them right here. And as you can see already, the actuator makes up most of the space. So the purpose of the actuator is to transform the electrical energy into mechanical movement. So you can see it down here. We basically need to have a linear oscillatory movement to oscillate the membrane right here. So for that, we develop our motor, our actuator, and I'll get into that in a bit more detail later on. And then we have the pump head right here, which is volume-wise the smaller part, which is, simply speaking, a membrane, a disc-shaped membrane between two flasks, and it accelerates the fluid from the outside to the inside. So the way the blood flow comes is it comes from the top, from the heart. It makes its way around the actuator. The actuator is sort of a cylinder. It's, so the blood flow is around it until the edges of the pump head where the membrane is fixed, and then it is accelerated towards the inside where there's an outlet and the fluid, the blood exits through here. So I have a small animation which shows that. It doesn't show the blood flow very well on the outsides here, but you see it comes in from the edge, is accelerated to the inside, and ejected to the side. So this is what we build. We have we continuously optimize our design, and the way we characterize our pumps is we have test benches which we developed. We do our own metrology, our own characterization. So here you see a hydraulic test bench which allows us to characterize the pump. We use water glycerin mixtures to approach the density of blood. We have pressure sensors included, flow sensors, temperature. We can control the temperature. We measure the displacement of the membrane through a laser. We measure the electrical consumption, and with all this data we can measure the hydraulic output, the efficiency, and all that. And in the end, it allows us to extract classical pump curves. This is nothing else than a pump. So this is for those who have ever worked with pumps or have ever had to dimension one. A classical HQ curve, which are the blue lines. So you see pressure dependency in function of flow, very classical characteristics. On the same chart, you can also plot the hydraulic power in function of flow. Well, and then we actuate our membrane at different frequencies. So here you see 60 hertz, 80 hertz, 100 hertz. So this is the frequency of actuation of the membrane, the frequency of oscillation of our actuator, which does a transmission from electrical energy into mechanical. Now, if we look into the efficiency of the system, I wrote here we are continuously improving it. We are in the range of 16%, anywhere between 15 and let's say 20 max, which we can get under laboratory conditions. I put in this slide to explain to you a bit where our current losses are. And this is a typical figure actually for all LVADs in the system. Typically, the actuator is 40% efficient, and we have 40% of losses in the actuator, and you have 40% of losses in the hydraulic path. Now, the actuator losses are essentially twofold. We have coils, we have copper coils in the actuator, which are necessary to induce the magnetic field. There's a constant current flowing through it, so we have resistance losses through the copper. This is something which is difficult to avoid. Well, if you induce less current, you will have less of these copper losses. But this is a major contribution in the actuator losses. And then we have so-called iron losses is through the magnetic field which is generated. Some of the magnetic field is dissipated in the iron material which makes up the actuator. And so those are the losses in the actuator. And then we have the hydraulic losses, which I wrote here, well, which they are the dissipative losses in the fluid, which is something probably you are aware of, which is much more difficult to optimize because it's much more difficult to pinpoint exactly where these losses occur. So when I was preparing this presentation and had to write the abstract, I was thinking about what would be the most interesting to present here. So this sort of concludes my introduction. And what I wanted to highlight is all the different fields of engineering which this development touches. So we have on the one side mechanical engineering, and we have what I call the classical mechanical aspect, which are the kinetics of the system, how it moves, the oscillation, the resonances we see. Then we deal with more classical solid mechanics on the fatigue side of view. So you see we have a relatively high frequency of oscillation, 100 Hertz. These devices have to last for at least 5 years. So these parts see a large number of cycles. So this is something which actively keeps us busy. Fluid mechanics, obviously, fluid structure interaction between the membrane and the fluid, and how to increase efficiency on that point. And these aspects are probably the most pertinent to this audience. But then we also have quite a bit of electrical engineering, so classical power engineering, motor design. We're designing our own motor, or I should rather say we're optimizing our own motor. So we're carrying that out by ourselves. We have the power electronics or the electronics of the control system. How do we control the system? Signal acquisition in electronics, and then biomechanics, which is hemodynamics. So the impact of the system on blood, where we actively carry out hemolysis experiments on a continuous way. And physiology, something I will highlight in this presentation too, is the interaction of the pump with the natural pulsatility of the human body, because, well, it creates some additional complexity. So I'm going to pick out a few of these and just describe the topics in general terms, so you can see what we're dealing with. So the first one is, or the kinetics of the system. How is the kinetic behavior of the system? How does it behave over the frequency range? And the easiest way to represent our system in a model is this, where we have an electrical model on the left, which represents our motor. And the easiest way to represent that is just by an RL system, a resistance and an inductance. And then on the right, we have the mechanical model, which is in its easiest way just a spring, a mass, and a damper. And obviously, this simple model has limitations already on the electrical side. We can describe our actuator better than this RL model, but that starts presenting a range of other problems if one wants to solve the system in the frequency domain. So often we just stay with the RL model. And on the mechanical model, if everything is linear, a harmonic oscillator, well, it's a well-known problem, and you just have to fit your parameters, and you can see if it works. And this is something which we do in tests without load. So where we remove the membrane, we actuate the membrane or the actuator in air. There's no load applied, and we can fit experimental curves to this model, and the values which we extract for the mass of the moving part and the spring are reasonable physical values. part of the limitation is then, though, that there's no hydraulics included in this. The hydraulics are lumped into our dissipative factor, our damper, but it's difficult. We extract a certain value for it, but we don't have a direct link to what does that mean in terms of hydraulics. And, well, this is what I mentioned before, that we're not including the iron losses in the system on the side of the actuator. So this is the very simple case, but obviously things are a bit more tricky. And I'm just showing as an example the Duffing oscillator. I'm not showing any equations here on purpose because I will probably make a fool out of myself with this audience. But just to let you know that we witness nonlinearities in our system, we look into them, and this is what incited me to contact Arnaud and his expertise, and for him to help us understand the frequency behavior of our pump, well, in an environment with a load and like that. So the Duffing oscillator, just as a reminder for those who might have forgotten, it's the Duffing. It's basically a system which is where the spring is nonlinear, and what happens is that your resonance peak is then shifted to the right, and you have jumps. You have instabilities. You have jumps. You have hysteresis, undesired harmonics, and these are things which we are looking into, and together with Arnaud. Then the other part I wanted to talk about is more solid mechanics related fatigue. So as I noted up here, we have an oscillation frequency of around 100 Hertz. Now, these devices have to last for at least 5 years, and if you run the numbers, you have 10 power 10 cycles, which is 10 billion cycles. I mean, it's a large number of cycles, which the membrane sees, and also the membrane is held into place by what we call springs. They're thin metal discs, essentially, which basically keep the recoil effects and transform our kinetic energy into potential energy and basically keep the oscillation going. So on the membrane side, we're collaborating with Cermel to evaluate how much strain we are allowed in the membrane, so we would assure infinite lifetime, or at least 10 billion cycles. And so by strain, this accelerated testing, by straining them more, and then we can extrapolate that, well, if we keep our strain under 5%, which we do, from a purely material point of view, the material should be able to last. And then on the springs, I'm just showing a classic Ascent Curve. There's no data in here, but where also we pursue a similar approach where we come down the Verla line with accelerated testing and try to reach this point here where we have infinite lifetime of the springs, because this will define by how much we can displace the membrane. So that's an important factor for us, is what is the actual displacement of the membrane, what we call stroke, by how much does it go up and down, and by knowing how our springs perform, well, we can define this value. So there's the inherent material properties which go into here, but I would like to point out that it is a bit more complicated. Obviously, we can design. We have an influence of design on these springs, on the membrane to a certain extent as well. And then we have a big part which comes into making the parts, machining the parts, which influences the material behavior, and then also the assembly process, how are the parts assembled and what are the boundary conditions in that system. So all that comes into play and has an impact on fatigue, and then afterwards well, what are the failure modes, crack propagation, stuff like that. So these are things which keep us quite busy. Another aspect which I would like to highlight is fluid structure interaction, where we're currently mostly carrying out, well, no, it's actually two equally. We're doing visualization of our membrane through transparent housing. We try to see how does the membrane actually behave to see it, to visualize it. This is what you can see here with the help of a high-speed camera, because then with the grayscale we can extract what the Z displacement is, or the vertical displacement of the membrane is, and how that behaves. For example, in this case, we see it is not perfectly symmetric, which may be due to how the membrane was manufactured, or to how it was assembled, how it is constrained on its sides. And then we're also carrying out simulations, CFD simulations, to figure out where can we, or how can we improve our hydraulic efficiency, avoid recirculation zones in the system, because those are problematic from a blood compatibility point of view. So these are our activities in that domain. With this, I would leave the mechanical engineering domain and talk a little bit about electrical engineering. In my group, as I said, we also carry out the optimization of the actuator. As I said, it's a transformation of electrical energy into translational movement. For this, we use a so-called linear synchronous motor. It's not your classical asynchronous three-phase motor, because those are used to rotate things. We want a linear displacement, and we want to avoid having a gear where you have to transfer rotary movement into linear movement. Well, this is the equivalent circuit for such a motor. And then we carry out electromagnetic simulations to improve the geometry of our actuator. Here you have the yellow and red parts are the areas where we have the copper coils, the coils which generate the magnetic field through the AC field. And the blue is the iron material, which leads the magnetic field to the outside to what we call the magnet ring here, which is the moving part. On the inside here, we have the permanent magnet, which actually induces the movement. And then when we do this optimization, what we're essentially looking for are force position curves. So how much force can we generate with this motor at a given position? Because we move the magnet ring, and if we're further up, we generate less force than if we're in the center position. And well, here I'm going to repeat myself with the losses which are associated to the motor. The other thing I mentioned is the impact on physiology of these systems, of this LVAD. Because what happens is, when an LVAD is implanted into a patient, an additional parallel circulation path is created between the heart and the aorta. There's a direct path between the heart and the aorta, but when we include an LVAD, there's a second parallel path which is included, and which complicates the dynamics of the system and of the human body, and the impact on the pulsation of the body. And this is where we use so-called mock circulatory loops, which simulate how our heart works and has the appropriate hydraulic resistance of a body, and control chambers which compensate for the pulse induced. And then we can plug in our pump and see how it impacts for example, pressure difference in the body after the heartbeat. And then we can run different experiments, and I'm going to go over this quickly, at constant speed. So we can also actuate our pump in continuous flow, like the rotary pumps. But then there's different pulsation regimes which can be looked into. One is copulsation, which intuitively one would think would be the most natural. One synchronizes itself with the pulsation of the heart and pulses at the same time. But the whole story is quite intricate, in particular to this additional parallel path. The other extreme option would be counterpulsation. One pulses exactly at the counter moment of the heart, or one can try and dephase the pulsation of the device and the heart. So this is something which is actually keeping researchers busy since a number of years in different institutes, is what would be the best way to operate a pulsating device. I think part of the problem is that it's not really known, is that because there's no truly pulsating device on the market or even available for testing, animal testing, to see what the true impacts would be. But it's not that trivial trying to decide how to pulse this device. And then I touched on well, the blood compatibility of the pump. We have continuous testing going on at CorWave, where on a weekly basis we test our pumps in different configuration to see the impact on hemolysis. Hemolysis is blood destruction. So obviously we're introducing a foreign device to the body. There's a movement involved in it. It's foreign materials and everything. There will be a certain amount of blood destruction. However, I mean, one has to minimize it, and that's what we're evaluating on a continuous basis. Now, I'm just forewarning you. I'm going to show you one image of an animal trial. So if you're a bit sensitive, you're forewarned. Show you our current progress on those aspects. So what you so we are in the phase of carrying out chronic animal trials on sheep. We do this in Belgium, in Leuven, because there's a big center there which has lots of experience on early evaluation of LVADs, which are still in research development phase. Here you see how our device is implanted underneath the heart. And here is a sheep after surgery. You see the percutaneous lead coming out. We have remote monitoring, and currently we're able to keep the sheep alive for at least 8 days. We're still we euthanize them afterwards because it's important for us to see how the pump looks after it has been in the body, because one aspect which is very difficult to test in a lab is thrombus formation, so coagulation of blood particles which can provoke clots and then strokes in patients inside the pump. So that's why we want to get them out still from when the animal was doing well. And all our first indications on that respect are that we do not observe significant thrombus formation, and these are good indications. And right now we're in the process of extending our animal trials because this first concern, we could eliminate. Just to show you how the field is, or how the field is structured down here, and how it evolved down here. These are the conventional rotary pumps, and there are quite a number of projects which are in preclinical phase, clinical studies, and commercialization. However, what is interesting to see here is that for the conventional rotary pumps, there is essentially only 3 devices which are really established. It's 2 devices by, used to be Thoratec, which was bought up by Abbott, HeartMate 2 and HeartMate 3. And 1 device from Medtronic. They have essentially, easily over 95% of the market. All the others have the approval, but they're a really small player in the field. So this is a field which is very concentrated in 2 players. This is a different type of technology to support the heart, the counterpulsation. There are a number of companies who are working on smaller pumps. They're still relatively big, I would say. If one shows these pumps to a patient, they're about this size and this high. Patients are always taken aback by that. So there's efforts ongoing on reducing the size. However, you see even for established companies, many projects have been abandoned just because it's a difficult problem. And as you could see from my presentation, the biggest space is taken up by the actuator, and then you have to get the blood to flow around it too. And then for pulsatile technologies, and also which are miniaturizable, there is not that much out there. Most of it is in research phase, and we're the only ones who are in preclinical studies with our 2 products, which can truly provide pulsatile conditions, which all these others cannot. And that's what we're essentially, what our mission is, to provide true pulsatility and to distinguish ourselves through that fact. And and help the patients avoid these severe side effects. So this concludes my presentation. These are a few images of the team. We are located in Clichy, just outside of Paris. We just moved in there in the fall of last year. Before we were located in an incubator in Cochin, not too far from here. We needed to move out for space reasons because, I mean, as I said, we're over 45 people right now, and also because we have set up our own tool shop to make lots of these pieces which we need for the prototype development and our characterization test benches, and well, yeah. So that concludes my presentation. I'd be happy to take any questions. And as I said, I'd be happy to switch in French. It's just easier to go through in English for me right now still.
Thank you, Brian, for this nice presentation. It's a little bit different from what we are used to, but I think it's also changing a little bit. So if you have any question, ouais.
Thank you for the presentation. How do you keep your device in synchronization with the blood flow or the heart pumping?
There are several ways to do it. Just trying to think of how to structure my answer. I would say the most straightforward way to do it is that they are, to a certain extent, integrated sensors in the pump already, meaning the electrical signal. By measuring the electrical signal, one can measure if there's a flow acceleration or deceleration through the pump, because it influences the load on the pump, and you have a signal on your electrical signal when the heart is pulsating. And this we clearly see. All the other devices also see it as well. It's basically you change the hydraulic load. So that's one way to do it without introducing an additional sensor, which one would want to avoid. There would be another approach, which would be a bit more complicated, but one could think about is sort of synchronizing the device to something like a pacemaker, which triggers the beating of the heart. So that would be the other approach. But that's how one would go about it, one or the other. And typically the approach is to use the signal which is on the electrical signal.
Thank you.
Yes, you said that you tried with water and a mixture of water and glycerol to mimic blood, and then you test on a chip. But do you test with real blood before going to test on animals, or yeah?
Yes, sorry, that probably wasn't clear. What we do in our group, because we're very much focused on what I call the implant development, which is the pump, we do the hydraulic characterization, so the pure performance characterization of the pump of the implant in water glycerol mixtures. Then we give the pump to our so-called blood team, which does hemolysis testing. And so twice a week we have hemolysis tests which are carried out. These are tests which take 6 hours. On the implants to determine the impact of the hemolysis, and once we have a configuration which doesn't produce excessive, well, which is good on an hemolysis level, then we proceed to the animal trials. And something, just to complete the answer, give a bit more context, what is very difficult to do, so the hemolysis can be done very well in the lab. What is very difficult to do in the lab is to detect thrombus formation. And that's why you need the animal trials too. That would be the third step then.
So, yeah, maybe just one last question about the biocompatibility. Right now, it's made of a certain steel, and I don't know what kind of elastomer for the membrane, and that's all okay for getting in the body for 5 years, or?
Yeah. So. In the end, the only materials the body will see are titanium. So everything which is not the biocompatible materials, just for example, our copper coils, will be encapsulated in titanium, because titanium is very I mean, all the other devices are in titanium. It's just the best material for biocompatibility. Then we have the membrane, which is a type of a silicone, but which is a biocompatible material, FDA approved. And what we don't know yet is that there might be some stainless steel on the inside, just for parts which we can't make out of titanium, but also this stainless steel is biocompatible. So there's only 3 materials which will actually be in contact with blood: biocompatible stainless steel, titanium, and the biocompatible silicone. And everything else has to be encapsulated and hermetically sealed, which presents a whole range of challenges on the manufacturing and process point of view. Afterwards, you have to prove that it's hermetically sealed. You do helium leak tests. It's quite involved because you have to prove that nothing can penetrate to the inside.
Thank you. So if no more questions, thank you again, Brian. And
thank you.